Good afternoon, and welcome to the 54th Annual James R. Killian Jr. Faculty Achievement Award Lecture. I'm Roger Levy, Chair of the MIT Faculty. Before we begin, I'd like to request that all electronic devices be silenced. Take a moment to do that. I want to see you all doing it. I'd like to request that all electronic devices be silenced. And I'd like to invite those of you on the edges of the room to move toward the middle of your rows so that we can accommodate those who may join us after the lecture begins. So I'd like to see some people do that too. Great. Thanks so much. The James R. Killian Jr. Faculty Achievement Award was established in the spring of 1971 as a permanent tribute to Dr. James R. Killian Jr., president of MIT from 1948 to 1959, and chairman of the corporation from 1959 to 1971. The Killian Award recognizes and celebrates extraordinary achievement by MIT faculty members and communicates their accomplishments to members of the Institute community. The title of Killian Lecturer is the highest honor that the MIT faculty may bestow on a colleague. It is our privilege today to be addressed by Dimitris Bertsimas, the current Vice Provost for Open Learning, the Associate Dean for Online Education and Artificial Intelligence, the Boeing Leaders for Global Operations Professor of Management, and a Professor of Operations Research. Professor Bertsimas joined the MIT Sloan faculty in 1988, immediately after earning his PhD from MIT. He has served as the inaugural faculty director of the Master of Business Analytics program since its inception in 2016, previously held the position of Associate Dean of Business Analytics beginning in 2019, and has served as Vice Provost for Open Learning since 2024. Professor Bertsimas' scholarly contributions are both extensive and groundbreaking. He's one of the rare individuals who have made significant contributions to both intellectual threads in the field of operation research. One, optimization, combinatorial, linear, and nonlinear. And number two, stochastic processes. His numerous contributions include fundamental advances in queuing theory, approximation methods, combinatorial optimization, and machine learning. His pioneering work in robust optimization has fundamentally reshaped the landscape of optimization and decision science. Robust optimization has become an essential tool in tackling problems involving uncertainty across diverse domains, including supply chain management, healthcare, finance, and energy. This body of work culminated in his being awarded in 2019 the John von Neumann Theory Prize, often regarded as the highest honor in the field of operations research. This is but one of a very long list of top awards and honors Professor Bertsimas has received, a list that includes his being elected to the National Academy of Engineering in 2005 at just 43 years of age. Professor Bertsimas' contributions further range beyond traditional theory-based domains of operations research to a broad spectrum of applications. Just a few examples among many include optimization of financial portfolios, school bus routing for the Boston Public Schools, supply chain optimization for fertilizer production, medical data mining for advising on critical care management, daily use of electrical generators in New England, and personal diabetes management. Beyond his academic work, Professor Bertsimas has co-founded several successful companies that have translated his research into practice. Throughout his nearly 40 years on the MIT faculty, Professor Bertsimas has integrated his tremendous accomplishments as a scholar to his role as an educator. His courses, including the massive online open course, The Analytics Edge, have educated and engaged hundreds of thousands of students across the world. Professor Bertsimas has also co-authored 8 leading graduate-level textbooks that reflect his diverse portfolio of interests, including optimization, queuing, analytics, and machine learning. He has supervised, and this is one of the most mind-blowing numbers to me of everything I'm going to say here today, 106 completed PhD dissertations, with another 19 currently in progress. And importantly, Professor Bertsimas was also the main force beyond the most transformative development that has taken place at MIT Sloan in the last 25 years. The creation of the immensely successful MBAN program, which is the top-ranked analytics program in the world and is now being replicated at management schools globally. Dimitris, will you join me at the lectern, please? Here we go. Professor Bertsimas, it's my privilege to represent the MIT faculty in honoring you with the James R. Killian Jr. Faculty Achievement Award. In doing so, we recognize your intellectual breadth and accomplishments, contributions to theory and practice, and educational leadership through which you have made a lasting impact on your profession, the Institute, and the world.
Thank you.
Congratulations.
Thank you. Boy, I thought you would go on for the lecture. Oops. What's going on? Thank you for coming. So I need some help, huh? It used to work. Okay, so I'll start my remarks anyway. So first of all, it is a privilege and an honor to be in the long history of my predecessors, 4 of which I have recognized: Professor Paula Hammond, Professor Robert Merton, Professor Maria Zuber, and Professor Sally Chisholm. I have to admit, I know the previous because I studied it. I'm honored that you are. Yeah, I have to admit, in coming here, well, as you know, it was a repeat because we had, the SNO did not collaborate. I sent my files and it got corrupted. And then I started here and reproduced the lecture sort of, in the last hour. At least it works now. Hopefully it will be last in my. So in thinking about where is the gentleman got the. Okay, so in thinking about what to talk today is I thought about a topic that will appeal also to my younger friends, younger audience. I'm sorry for the less younger audience. So I thought to talk about Algorithm for Life and tell you a bit about the trajectory of my career and research and education from when I joined in '88 and when I was a student in '85 until today, but with a view towards the future. So there's a lot of information that is far more recent as opposed to only celebrating some of the material that brought me to where I am today. So I will start with some personal reflections. I will talk to you about the evolution, my evolution from operational research to analytics and AI. I talk about robust optimization, perhaps my most cited work. And then I talk about healthcare, agriculture, and education, which occupies my thinking quite a bit these days. You heard that I'm the Vice Provost for Open Learning. And then I have some remarks on the future. So I've been 41 years at MIT. I came as 3 years as a student and 38 years in the faculty. So it's about 2/3 of my life and counting. Now, MIT is part of my identity. This is not, this statement, you should take it literally and figuratively. Figuratively, 41 years, of course, is a part of my life, but, and I checked, MIT has about 1,100 professors. This is a rarity. I haven't found one. There were previous before, Dimitri Antoniadis, Dimitri Bertsimas, but current faculty I haven't found. So I have some unique characteristic, at least I found one. So in thinking about what to talk about, this is something that occupies my thinking a lot of time. I mean, what matters in my life? And because for me, research is not how to do something. It is an extension. Is there a, yeah, great. I became too static. So, oops. So what I aspire to do is through research, education, and entrepreneurship, I try to improve the human condition. I aspire, doesn't mean I do it, but definitely I aspire. I try to increase the human understanding of how the world works, and this is this talk. It's an unusual academic talk, but you will see. And I also try to positively affect my young friends, the young people. That's a significant portion of my daily life. In fact, I heard I supervised 19 students, 18 of whom are today in the room. Speaking of young people, it is far and away my most favorite activity to supervise my doctoral students. You heard that I have increased it to more than 100, and because I love it. It's not something I do it because I have to do it. I love it. It is a privilege, in my opinion, to work with exceptional young people like the ones we have at MIT in ability, in character, and aspirations. They actually make me a better scientist and a better person. They actually help me to increase my happiness. There are, in my opinion, two things that are important. Happiness, the first is to find somebody that you love, check. And, and second, to do something that you love to do. And definitely working with my students is something I love to do. They help me achieve what Steve Jobs in the graduation talk in 2005 at Stanford said, stay hungry and stay foolish. So to demonstrate a little bit about the connection, yesterday night we had my group, and my group gave me this present, and I would like to, it's touching that the way I use the term my young friends, and obviously they learned it. So now I would like to talk about the evolution of my field and to give you a bit of a sense. So pre-2015, I was working from structured data to machine learning models to prediction. This is basically what currently is called data science, analyzing data. But that's sort of a field. There are multiple programs in the world in data science. My field in operational research, where I started, starts with models, typically optimization models, to decisions. But the union of these things is called analytics. And in fact, the Master of Business Analytics is one of the first of its kind at the time. Others have existed then. That combines data science and optimization together. That's not typical. So, and that's a signature aspect of our program that attracts externally strong students, and unbiased perspective, of course. So post-2015, something has happened. What has happened is that in addition to structured data, we also have unstructured data. In other words, images, language, genomic information, not numbers, in other words. And we augmented the notion of a model to DL, deep learning, and LLMs, large language models. These are terminology you hear in the last couple of years very often. So the union of these things, I call it artificial intelligence. This is my personal definition, but I think I'm not off by a significant amount. And our current efforts, in my role as Associate Dean, we try to infuse AI to our core offerings at the Sloan School, the Master of Business Administration, MBA, and the Executive Master of Business Administration. So what I would like to talk to today first is what started. And in every of these cases, the way I think about the problem is not I sit on my office and I think, let me now prove something. It's not my style, people who know me. I try to be motivated by problems I see in the real world. And this was a case. So there's actually an interesting history about that. So in 2000, I would say 1913, the US government took the responsibility to build the Panama Canal. Has anybody been to the Panama Canal? Yeah. Good. It is an engineering marvel. I mean, it's not something it's a very unusual place. So the US government took the responsibility of managing the canal until the year 2000. And in the year 2000, the Panamanian government had got the responsibility. In 1998, I got a call. I mean, I'm reasonably knowledgeable in optimization. Somebody who knew that I knew and I liked practical problems approached me in 1998 to help them develop an algorithm for the Panama Canal because the American government were afraid that we give control, then what? You know, a big portion of the world's the number of ships that go there is a sizable portion of the navigation system of the world. So the Panama Canal combines the Atlantic and the Pacific Oceans by locks, right? And they were doing it manually. So my responsibility was, together with a student of mine, to actually create an algorithm that does that. And we've done it. And I go back to Panama to present this great algorithm this great MIT professor developed. 1,000 people, the minister of, I think the vice president of the country came. This is big business for the throughput at the time was 42 big ships a day, each ship 300,000. That's sizable amounts daily. So I present. I was very proud because we increased the throughput from 42 to 48, right? Completely automatically in seconds. And then in the end of the talk, somebody says, Professor, what happens if the boats that push the big boats break? I said, oops, I didn't think of that. So it wasn't a fantastic ending. So I go back to Boston, and I said, I should do something about that. That's an embarrassment. So then, in the next 2 slides, I forgive you if you don't follow. All right? There are 3 slides. But this is an example of a constraint. In our world, believe me, it's going to be uphill after that. The mathematics is only there. But I have to tell you what on earth robust optimization is. So you have a constraint that has numbers. These numbers are estimated, right? These are rates and so forth. And the number 859 is estimated. The actual number is estimated to be larger, 859, 8819. There are some numbers, like the number 1 in red, that is known. But the complication is the following. If you solve this problem with optimizations, what we have done since George Danzig in 1948 invented the simplex algorithm, you find a solution. This is a solution of, you know, in the Panama Canal setting is which ships goes at where at what time. Now, the complication is if these numbers are slightly inaccurate, like 0.1 inaccurate, at the very least, you need to have a feasible solution. The canal should run. Well, it doesn't. Even a little mistake can make the solution infeasible. 50% of the time, it is infeasible. And sometimes vastly infeasible. That's not a good thing, because you might, in a real world system, you might not be optimal, but boy, if you are not feasible, good luck to you. So, in fact, this is not an isolated problem. In a collection of problems that people use, about 1/3 of these problems were infeasible for very small perturbations, and about maybe 20% of the problems, the solutions were infeasible greatly. In other words, this is a topic that is relevant. It's not in my head, in other words, right? So, fasten your seatbelts. This is the complicated the slide, but I have to say something mathematical for my friends. So what is a constraint? A constraint is you have variables, x1, x2, these decision variables, and numbers. A1 is like, remember the constraint had some numbers, and we want to be feasible. Well, to do that, we say, all right, here's what we're going to do. We are going to consider perturbations. P is a matrix, Z is a vector. So it would like to be feasible for some perturbations as long as the perturbations are small. The norm is small, right? Okay, and it turns out that this is a very tractable problem. Even though it looks like an infinite number of constraints for all parameters, optimization beauty suggests that this is a trackable problem. The optimization problem becomes trackable. So this is now a methodology of the type that we have seen. You have a problem that is, you make it feasible and it's easy to solve. In other words, you don't have to run, it ran before it ran in 5 minutes, now it runs in 5 minutes and a half. So it's basically similar. And in addition, it has a nice guarantee. This is the second, and I apologize for that. If you have there is something you can prove mathematically, namely that if the perturbations are random, no matter what the distribution is, you can actually bound how infeasible the solution is. And the guarantee is independent of dimension as well as the distribution probability. You might say, well, this guy is smoking something. But this is actually an important result, because it has characteristics that in practice, you don't know if there are distributions. You don't want guarantees that matter of the dimension. You would like things that are independent of all this. And it has all the right ingredients. So you already remember Dimitris, huh? MIT. Huh? There's another instance in my name. The most cited paper of mine is Bertsimas and SIM, Operation Research 2004, that it was, and you see SIM as inside my name. It seems that two most important things in my life, among the most important, the Institute and one of my Melvin SIM is inside my name. I don't know. I was trying to find other connections. I'm done. So what is it, the price? In other words, if we apply this, we eliminate the infeasibility phenomenon completely. And the price we pay is relatively small. For small uncertainty of the data, we pay with only 1% optimality. We give up a little bit of optimality to be always feasible. So what happened in the Panama Canal? What happened in the Panama Canal, the deterministic problem went from 42 to 48. That's 300,000 times 6, 1.8 million a day, about half a billion. Well, robust doesn't have this, not as good, but it's 45. It's still half that, about 3 vessels, and this was what was implemented. So I would say it taught me something, that the problems, at least my motivation, started from practice. There was some mathematical theory, but the most important is that when you apply to real problems, something good happens. So that's sort of my past. Okay, so now I'm going fast forward in the what we are doing at the moment. So I would like to say also, I will tell you how I was motivated with the Panama Canal. This was motivated by a personal story. In 2009, I lost my father to cancer, to stomach cancer, in March. In fact, this week, 17 years ago. My aunt from diabetes in May, and my mother in August. It wasn't exactly the best year of my life. So, and while obviously I wasn't able to help them, I thought I would at least dedicate a portion of my career to try to develop things I understand to help people with this type of conditions. And an interesting story also motivated me. I don't know if you remember, in 2013, IBM had IBM Watch on in the game of Jeopardy. I'm terrible in Jeopardy, but it's because it's the right time. When we go home often, I watch it. I can answer, if I understand 3 questions out of 100, that would be a record. But I find it interesting. That day, 2013 and 14, I came early home to watch both games. Has anybody watched that game? Only 1, 2. I recommend you guys watch it. It is inspiring. A machine obliterated the 2 best players in Jeopardy. It was not a close match. So I was inspired. I said, boy, this is a new era. And I remember healthcare. Of course, IBM also thought they would do healthcare and so forth. Unfortunately, it didn't go very well. They didn't have all the ingredients. So a few years afterwards, I tried to implement what IBM thought to do, namely multimodal AI. If you think about it, we as humans, how do we perceive the world? You today perceive the world multimodally. You listen to me, you obviously see, so sight, hearing, smell, I don't think is relevant on that, taste and touch. So, humans, that's how they perceive the world. And small babies who have, over 2 years, they use all their senses. So it's not unreasonable that, given that multimodality is a fundamental characteristic of human life, that we can perhaps use ideas from computer vision, language, and tabular data and apply it in medicine. There are courses at MIT in computer vision. They're in language models, tabular, machine learning, and so forth. This year, a young colleague of mine, I have only 4 lectures on that, we have a new class on multimodal AI. So Paul Young is, from Media Lab is the gentleman who is leading the effort. So, we developed what I call holistic AI in medicine, HAIM, which is a Hebrew word for life. Another thing you see that I also like, I like acronyms. Sometimes when I think that's my contribution, my students do all the rest of it. I find the title. All right. So let's I'll try to give you the key idea of HAIM in one slide. So we have, what data do we have in? So imagine yourselves when you visit the doctor. You have electronic records, often. You have perhaps time series because you visited in the past. You have images, CT scans, MRIs, and so forth. You also have notes, radiology reports, nurses' notes, and so forth. And you have all this data, and the doctor makes a determination of what you have and so forth. And in my view, if I think if the doctor doesn't use this and the other, I actually feel a little bit uncertain. Has he or she did the best he could? Well, let me tell you with this what architecture we use. So let's say in medicine, you would like to make a prediction about do you have a particular disease, right? Lung cancer, as an example. Well, you have images, X-rays. So how do we do that? We run deep learning models, and they summarize the data, they summarize the image in a vector of numbers, 768, okay? So in the end, what happens is you have the image, and you get an embedding, a vector of numbers. That's a summarization of the image. You have language. Again, you run it through a large language model. The ones we use was called BERT, that does not stand for Bertsimas. And you get another summarization. You also have electronic records that they are numbers themselves. So it's already there. You take all this data, you concatenate, and use classical machine learning. You have now instances of all these numbers. This particular patient has cancer, the other person does not have a cancer, and so forth. You train a model using machine learning methods, and you have now a prediction. So this is very general. It can apply to all of medicine. It can apply to many other fields, but medicine in particular. Because if you want to, for example, understand whether, for example, the person, what is the probability of dying in the hospital, not a pleasant thing, but it's useful to know, it applies. It takes all the data, and then, so it's a very general technology. We published a paper in 2022 in Nature Digital Medicine. Again, this is, as I told you, very recent stories. So now I have some applications of this, because the applications are endless and very exciting in my view. Of course, it's from a biased perspective. So we applied in a recent work. We just submitted the paper, actually. We tried to detect what's called subdural hematoma. What is subdural hematoma? Bleeding. Suppose somebody has an accident. You are rushed in the hospital. Is there bleeding in the brain or not? If it's not detected, the person will not make it. If it's detected and something is done about it, surgery typically, the patient might live. So it's the problem. The first problem is diagnosis. Is there subdural hematoma in the brain? And you have to do it fast, because time is not in your favor. So now, we basically utilize HAIM, holistic AI for medicine. We have a CT scan, we have tabular data, you have also radiology reports, perhaps previous electronic medical records for the patient. We can detect hematoma, and we can say, what's the probability that hematoma is there? Then localization of hematoma. We need to understand where it is. So you see here the red, the algorithm did segmentation and found where the hematoma is. Again, an application of HAIM. And this also is relevant for explanation. You might say the probability is 0.95, very high probability of hematoma, but the doctor would like to know, where is it? So this is what the method does. And finally, and quite importantly, progression predictions. And progression prediction says, what's the probability? Okay, you might have hematoma, surgery has, but sometimes the hematoma comes back next day, 2 days in the future, 3 days, and so forth. You better have a sense of how likely it is that there is the hematoma comes back, recurrence, because you have to treat it appropriately. and this finds what is called the right treatment. So this is we built an algorithm, and the algorithm is actually quite practical. It is very high accuracy on detection, not as high on progression, but it's the only available method today. So we are actually in the process of running trials with Hartford Healthcare. Hartford is a system that in the last 10 years I have dedicated a lot of effort. It's the largest system in Connecticut, 2,600, actually 3,000 beds, 9 hospitals, about $6 billion revenues. And the advantage of that we have a close relation, and all my students, about 17 of them, they actually have accounts, they use data and so forth. We have full access, and I think this is particularly exciting. It also provides an example of how MIT as an institution can also connect with other hospitals. It's not an easy task. I've tried it with MGB and I failed. So, but not at Hartford. Second application, very exciting in my view. What I call AI companion for differential diagnosis in the emergency department. Many of you have been to emergency departments. They are overcrowded. If you go to MGH on a particular day, you might wait 10 hours easily, sometimes a full day, actually. Now, is it possible to accelerate the process by using AI to help? And the answer is, this is our efforts. We call it the AI companion. We need a better name. I haven't yet. So I give you an example of a patient. I didn't select, I was not trying to impress you. I tried to give you a routine case that is relevant in an environment like an emergency department. It's a real case. So this is the characteristic of the patient, a 60-year-old white male. It's a former non-smoker. He had cancer. He had actually pancreatic cancer. He had a Whipple, which is a serious surgery. And these are the vitals. He also has a history of kidney failures, because when you go, what are the data that you want? You go to the hospital, they get your vitals, and you have triaged by the nurse. The nurse, you say, what is it that you do? You know, and they, in the record, the fact that he has adenocarcinoma and so forth is known, Whipple and so forth. But he also has other characteristics. This is directly from the record. The patient said he was not passing a lot of urine, but when he did, he passed a large clot. No blood thinners, no fevers. The temperature was 99.6 at home. Currently it's 97.8. No nausea, vomiting, more stool production, but no diarrhea. So this is a real depiction of what the nurse wrote, you know. And based on this is before the patient went to the AD. So what the method does, it basically says, based on this, I have an initial diagnosis. In this case, there are 3 possibilities. The details are not so important, but they have different probabilities and explanation for that. This is all machine-based. And in addition, it proposes which test to do. Currently, the story is all the data goes to the emergency department, the nurse, and after 2 hours, they have a diagnosis, then the person comes, they examine, 3 hours later, 4 hours later, they tell you about here's a possible exam. That's the current situation. We have gained 3 or 4 hours because there's no need for this, for all of the. So we completed these 2 tests, the complete blood count and the urine analysis. The complete blood count was normal. The urine analysis was abnormal. There is a discussion of what it found. The machine does that. And this is the final diagnosis. And you observe that the urolithiasis, whose the middle diagnosis, became very likely. And in fact, the ground truth was that, because we know the case. So this is an illustration of how the method could work in a real-world environment in the AD. And we are currently in pilots on that. And we, in fact, working with, through the MAGIC system, actually, with, boy, I always get the company wrong. Unisystems, how do you call it? Vasilina? What? Intersystems. It's one of the, to utilize it throughout their clientele in the system. So that's an example of something I'm excited about. Our claim to fame is that if we apply this methodology across a wide variety, we can find the 3 top diagnoses 95% correctly. We might not find the one, but boy, we have limited significantly. And a technical measure is what's called the uncertainty score. We make it a very significant drop. In other words, we do gain information by this process by using LLMs and optimization. So many other applications of HIME. In oncology, early detection and therapy. Obviously, I won't spend the rest of the time giving you this, but given I have a large group, you already heard it. We are engaged in many of these. For example, cardiology, a very exciting project. In fact, also related to a personal story. I had a cousin. You might say, my goodness, all the stories that I remember, but are relevant. 48 years old, we played together. Avram was his name. When he was 48 years old, second wedding, he went to the second largest city in Greece on a Saturday. He wasn't feeling well, went to the hospital. There was a doctor there, a young doctor, said, you look okay. He was a fireman, very healthy. They brought him to the hotel. He had a heart attack in the hotel, and this night he died. So we are trying to build a system that, based on an EKG, because that's the only thing they had at the time at 1 o'clock in the morning, to basically have, in a sense, an X-ray of the heart, to be able to see how likely it is and so forth. We have recently succeeded with a team, and we are currently in pilots at Harvard. Surgery. One of the most important is what kind of surgery, personalizing. Surgery, medicine generally is not personalized. That is, people they don't specialize to a person. But this is trying to use HIME for personalized events. Psychiatry, very exciting. This is actually a low-hanging fruit. There is not much AI in psychiatry. Well, we're trying to change that. So we have built a system that diagnoses multiple diseases and provides therapeutics. And a final project, this is together with my friends at MGB, intimate partner violence. It's not widely known. I thought that intimate partner violence, primarily against women, 99.9% against women, is a third world problem. I have news for you. It is a first world problem. This is MGB, 4,000 cases a year. So based on this, we developed a method that can understand, can detect IPV with very high accuracy, and then appropriate measures are taken. It's currently in pilot at the Brigham and the Mass General. And also something that my final application on health is something that's operational. So decreasing length of stay in hospitals. So this is a major story, both monetarily and from a perspective of health. So this is the scientific evidence. So what is length of stay? So somebody has stayed 4 days in the hospital. Is he going to be discharged or not? Right? And accelerating that is good for multiple reasons. So one is financial. I will talk more about it. But also the other hospitals is not the right place to stay there for long. You might get, not good things happen if you overstay your welcome. So we have scientific evidence. You use HIME to do all of this. All of this is good. And I use this example to also demonstrate something that I have observed. At MIT, we do great science. I'm not saying my science is great. My colleagues' science is great. But there is a problem in the story. We do the science, we publish a paper, and then what? At least in biology, with patents and so forth, we commercialize and so forth. But in algorithmic things, where patents are not really the name of the game, my observation was, if I want to impact the practice, which is my intention, not to write papers. I mean, it's good to write papers, it's good for the students also. But in the end, you have to make some difference. You have to implement it. So we started a company with Harvard Healthcare called Holistic Hospital Optimization, H2O for short, like the water symbol from my chemist friends. So that addresses length of stay. We have also deterioration index, try to find whether a person deteriorates early on without rushing to help the patient, and he might die from hypoxia. Personnel scheduling, room scheduling, and so forth, multiple things. I focus on length of stay here. So we have developed a method that explains why our prediction is what it is. We implemented it, and it improved length of stay from 538 days to 493. This is implemented in the last 3 years. It's not like it's their data, not ours. And to demonstrate the financial component, length of stay 538, this particular bed, if you divide 365 by 538, is 68 patients per year. Whereas if it's 493, it's 74 patients a year. And if the hospital is like MGB and so forth is extremely busy, 100% occupancy, there will always be a patient to take the position. So the 6 extra patients, you are going to actually serve by this bed alone 6 patients. If you multiply by 860 beds, which is Hartford Hospital, it's 5,160 beds, 5,000 more patients per year. So this is roughly 50 million more in the bottom line, because it's about $10,000 for a patient, if this is the current reimbursement from insurance. Hospitals like Hartford make 30 million a year, 40 million a year. They don't make much more. Some are negative. So we are talking at the same order of magnitude as the profitability of the hospital. This is not a minor story. It's not like you add 50 million to Google. That's 5 cents for me. But it's very different ballgame. So this is the second topic. I have talked to you about robust optimization. I've talked to you about healthcare. Now about agriculture. Why agriculture? I didn't say what, I didn't understand what he said, but. So agriculture, why agriculture? Well, I come from, my grandfather was a farmer. He actually, all his life, he spent in Greece, building olive trees, and that's how he lived. And my recollections as a child, and we still go, is that every season there was high uncertainty on the yield. Sometimes zero. Sometimes they get no money at all. Sometimes fantastic. On average, they can make a living. But unfortunately, life is not on average. You have to have every year. So it has also been in my mind that this is a significant problem, at least in the farmer environment that my parents grew. I actually am, my father inherited and I inherited. Of course, I gave it to my cousins. I know nothing about it. I have about 500 olive trees. My cousins have it. I don't even know where they are. but actually, if we combine my wife's olive trees in Crete, this will be a new career for us. All right. So what have we done? So based on this background, I thought, agriculture is not a minor business. The world is about 8 billion at the moment, and is expected by 2050 to at least double. So how are we going to feed these people? It's not a trivial task. So I was thinking, based on what I know, can perhaps improve that. And initially at MIT, and later with a company called Ground Truth Analytics, GTA, with 3 of my students, we set up to address some of the questions you see there. Specifically, we have satellite data. So the Ground Truth Analytics platform leverages multimodal data again, images, ground data, and atmospheric data, which is readily available. These are all publicly available, except we collect the data from the farmers with local motorcycles. We have about 4,000 motorcycles, 4,000 people that collect data in Africa. So we have satellite data, field data collected by ground agents, and atmospheric data. And currently the system we built is in 11 countries in Africa, meaning the only system that, in fact, the governments use it, this is almost unbelievable. The countries we are serving are agricultural. Most of their income, almost the entirety, is agriculture. Like, for example, Côte d'Ivoire, their major income is from cocoa. They sell cocoa to Swiss companies. Now, the complication is because they don't know who are the farmers. Nobody has. They cannot easily predict the income for the year. This is not a trivial topic, in other words. Well, so the question is, at the country level, what are the parcels of land utilized for agriculture? Second question, what crops are being cultivated? During the season, if you track the growth process of the plant, can you provide early disease identification? That's critical. This is exactly what happened in Greece. That is, we have the olives, but if there is a particular, how do you call it, parasite, and we go to 0, and you better detect it, you have 3-4 days. So understanding the growth of the plant is relevant. And finally, what fertilizers to use, protocols to use to maximize yield. That's not fertilizers. You might have philosophical disagreements, but boy, they increase production 50, 60%, right? So the ground truth analytics and the research before it addresses these problems. And at the moment, we have 11 countries in Africa that use it, and recently we have discussions in Europe and in Spain. I don't know about Greece, but Spain, I'm very optimistic. Good. So this is the last piece of my presentation is education. Well, on this, I don't have to have too many motivations because I've been an educator all my life. I mean, that's my principal profession. We educate young people here. And I'm quite proud of that. Even though at MIT, research and then education, in mine, they are equal. So I start with the following. This is relevant for the dream. I accepted the job of being the vice provost. The then provost, Cindy Barhart, somewhat tricked me in this. I didn't apply, in other words. I was in the committee. But in any event, I accepted gladly, and I'm very happy about it. So in fact, I would like to acknowledge my many friends from Open Learning that are here today, for many of which we work together. Clearly, this is a village, not one person. So, but one of my primary motivations is that, like what I do to the DIA, I give a lecture, is definitely not personalized. I mean, everybody hears exactly the same things. You see exactly the same slides. But in online education, you could see different things. You could hear different things. It is possible to do personalized. And I know for a fact that people have different goals, different interests, varied backgrounds, learning paces, different abilities. Even at MIT, this is true, where the ability is high. So I would like to give you my major aspiration. So we educate at MIT 11,000 students per year, but 1 in a million people, ballpark. We educate some of the smartest people in the world. I'm not trying to be, I know for a fact I have worked with 10,000 students over my career, not directly in teaching, 41 years, a lot of years. My aspiration for open learning and personal is to educate 1 billion people, 1 in 8. Everybody who hears me say that, I said, this guy Bertsimas, he took the tangent. I don't think so. But, so this is not, of course, it's an aspirational objective, but it puts some zeros on what we do today. So how do we do that? So here's a strategy. So we launch, and I take no credit for that because it was launched before me with my predecessors, but we launched, Open Learning launched, Learn MIT.edu, a new platform, July 2025. You should try it. We also launched Universal AI, how to teach AI to the masses, October 2025. We launched Ask Team, a tutor, in October 2025. This is in our past, a recent past, but in our past. We are launching Universal Climate and Energy together with colleagues from Climate and Energy, not surprisingly, with biology, health, but I hope by December 2026, we are in the process. And my hope would be we'll launch Universal X, meaning all departments, Universal Economics, Universal Physics. I have discussions with the chairman of these departments. Discussions meaning it's in the schedule, not theoretically. So we call this universal learning. So that's, in a way, universal learning aspires to bring MIT to the world, to create a movement at MIT, because it is not possible to get 1 billion learners if you don't get the totality of our force. Ballpark, my class, Analytics Edge 2013, led to about 1 million learners. We have more than 1,000 faculty at MIT. If you do the multiplication, about 1 billion. So no pressure to my colleagues. So to scale the MIT impact globally and also to democratize education. So these are aspirational objectives. We haven't achieved that, although our current is not bad. OCW, we have the open coursework, which is the 25-year anniversary, is April 8th. I bet it reaches tens, if not hundreds of millions of people. And it's materially relevant. I'm a fan. I might be the only fan, but I'm the fan. I'm a relevant fan given the. So so I'd like to tell you a bit about Universal AI. Universal AI is ongoing. Everybody at MIT has access. I recommend that you try it. About 4,000 people have tried it. It has, and it's involving about 33 faculty, mostly MIT, 2 or 3 visitors, visiting professors at MIT. So it teaches basic Python, it teaches data analytics and machine learning, it teaches prescriptive multimodal AI, generative AI, AI ethics, and so forth. Foundational, and then verticals. Healthcare, we have AI in precision medicine. Life, holistic AI, the HIME business in more detail, sustainability, AI and energy, AI and transportation. In fact, many people in the audience that have contributed to that. And we have multiple industries, and all of this is supported by something that I'm quite fond of. It was primarily developed by one of my doctoral students, Romain Push. It is basically capable of answering questions asynchronously to solving problems and so forth. It has been to about 20 MIT classes in the fall, right? We hope, and I will be talking to some departments, engineering council and so forth, to some of these developments. So this is in our past, so coming on the future, right? So this is towards the dream of personalized education, so customized education. So here I have a series of videos and audios, so I will rest. This will do the job, that do things that, honest to God, 5 months ago I thought it was not possible, right? But based on the exponential growth of large language models and the significant knowledge of my young friends, I learned this myself. In this particular case, I follow them. I don't lead them, you know. Thank God, because we do something. So, so this is a lecture from the Framing. I actually gave this lecture. I'm going to give you the entire lecture here, a small piece of the actual initial Universal AI lecture and how we customized it over time. In this lecture, we will present the Framingham Heart Study, arguably one of the most significant studies in 20th century medicine and cardiology. It is the study of using data and artificial intelligence to evaluate the 10-year risk of heart disease. That's a small portion of the lecture. It's about 30 minutes. So, using Gen AI, we can take this lecture and customize it in 5 minutes.
Today, we're learning about logistic regression by diving into a well-known medical dataset, the Framingham Heart Study. This tackled a really practical question. Will a patient develop coronary heart disease, or CHD, in the next 10 years? CHD refers to issues in the blood vessels that supply the heart muscle, and it's a leading cause of heart attacks. Our outcome is straightforward. It's either yes, CHD occurs within 10 years, or no, it doesn't.
So this is Dimitris AI. It's not me. I hope you got that. All right? So now, suppose I gave a lecture in a healthcare context. Can you customize it in a different context? Because universal means people have many interests. For example, energy. So this is customization to an energy content.
To create a failure prediction model, we need to identify our predictor variables, often referred to as features. These are measurable signals that indicate stress, aging, or emerging faults. A practical starting point usually involves what utilities already collect. For instance, recent alarm counts are a classic example. Sudden spikes in Buchholz relay events, temperature alarms, or cooling system alarms can serve as early warning signs.
Now, suppose you want to do it in English, in Spanish. Mind you, I don't speak Spanish. Although I checked with my friends who speak Spanish that this is good. So if somebody has disagreements, tell me afterwards, politely. So.
Vamos a considerar un caso típico en consulta. Una persona que viene para un control y ya tenemos algunas variables comunes de atención primaria. Hablamos de edad, sexo, presión arterial sistólica, colesterol total, cigarrillos por día, glucosa, y si está o no en tratamiento antihipertensivo.
I understood that part. Good. And final, suppose you want to customize multiple variables. Shorten, change the industry, and translate simultaneously.
Para que este enfoque funcione en mantenimiento, es fundamental que hablemos el mismo idioma de los datos. Una variable
Oh, you got it. Right. So we are actually planning. So we are launching translations April 2026, next month. We are launching customization. I checked with Ferdi, our engineering head, our CTO. He told me it's feasible, because sometimes he doesn't tell me that, but politely tells me, dream on, professor. Launching customization in Learn, MIT-DU, end of May. But this is, I have no doubt that this is within reach. When part of the Killian lecture, I say I will have egg on my face if it doesn't. I think it will happen. But I have a further dream. As I told you, the classroom instruction, by its nature, is not personalized. Online education allows personalization. I would like to be able to develop part of open learning, personalized education at scale. And we are actively working on it. In fact, my 19th student, who is not present today, is in Toronto, is working on this. In fact, I know this because he told me yesterday something we're working on. So we are hoping, what does it mean, personalized education? Somebody listens to the lecture, answers questions, and based on the answers, the lectures change completely, adapted to the person. If somebody told me this last summer, I would say, what is this guy smoking? It is within reach. I believe it's within reach. My final slide is something that I actually occupies my time for quite some time. There's no doubt that AI has transformative power. It's materially affecting all fields. This is, I would say, the degree might vary, but not the sign. Now, of course, in addition to health and medicine, we have seen in higher education, agriculture, we saw today, everybody works in this area. I bet, because our MIT faculty and students are very intelligent people, every aspect of MIT, 26 departments, centers, and so forth, work in science, in engineering, in economics, in law, drug design, transportation, and many others, humanities as well. So this is not a prediction, really. It's a very safe prediction that the fields will be transformed. But is AI capable of creativity? The very fundamental of MIT, we are a research institution. We produce new knowledge. And our current production process is through humans. We utilize PhDs. I overutilize the system in that way. But that's what we do. However, is this the only way? I have read recently that, I don't know if you know Terence Tao. Terence Tao is one of the strongest mathematicians of our times. He's a professor at UCLA, fields metal and so forth. But he has identified 3 problems of Erdos. Paul Erdos is a combinatorialist. I even know him for some years. He passed away. That were solved by AI. Solved. Not conjecture solved. I mean, these are not perhaps the deepest problem in mathematics. I cannot say that. But they are problems that defeated mathematicians, serious people, for many years. So in my opinion, this will change the identity of MIT. Not, because if you can develop things that are a machine can do, equivalent to what a PhD student or a mature researcher can do, we have to rethink what is our education system. So I'm hoping to investigate this question with the new crop of my PhD, which is my connection to we have open house at the Operation Research Center at April 2nd and 3rd. I hope some of them will be interested in this, so hopefully I have some answers, maybe not fantastic answers, but some answers in the years to come. I would like to dedicate the lecture to my past, current, and future students, of whom you see the last 20 graduations. So from 85 to 106. So I would like to thank many people who contributed to this presentation. People who know me, I don't know if it was an excellent presentation, but if it's an excellent presentation, due to them, not due to me. So Caroline in particular was fantastically helpful. My young friends being you, Vasilina, Cindy, and Carl, education on Romain and Diwang, and the agriculture, Dries and Daisy. And this is the end. We have about 10 minutes for questions? Yeah. Okay.
Thank you, Professor. Very appreciated.
Very?
I speak loudly.
Speak.
So I think it's great what you talk this kind of really interesting your trip and your journey from the data, AI, authorization. The next one, judgment, the responsibility. So what your comments on that? Do you think
Judgment, yeah. I definitely do not believe, I hope I didn't come across this way. Machines will do everything and we'll all vacate in Florida. I don't think that. I think, like our work at the Hartford Healthcare, we provide guidance. The decision is with humans. And that's how they do it. The way they do it is as follows. Early in the morning, I've been there multiple times. Early in the morning, they sort their patients by the probability of discharge next day. They talk one by one, and because sometimes the AI doesn't know many things. For example, one particular patient was, the AI said 99% probability of discharge. The doctor said it cannot be done. I said, why? Well, because we didn't identify where the patient will go. The system did not know this data. And this is an easy task. Sometimes these are not infallible systems. I have a saying that perfection is outside the human condition, and boy, it's outside the machine condition as well. So I don't believe that we as humans, we are going to release control. But I do believe we will be better off using it than not using it. That's my 2 cents. Yes?
I'd like to ask that, that those who have questions, please come to the microphone so that those who are watching remotely are able to hear the questions as well as Dimitris' response. Well, we have people. We actually have people who are being streamed. So
right,
I would like to ask the people. Yeah, that's perfect.
Thank you so much for the talk. It was really inspiring. I have a question. I'm a medical anthropologist, and I used to teach quite a bit on issues of racial and ethnic health disparities in medicine. And I'm wondering if you have found. So it's two questions.
One at a time, please.
Has your algorithm been able to perhaps reduce the number of, let's say, misdiagnoses, or have you come across cases where, because people may have certain biases perhaps toward the background of the patient, they may not prescribe, let's say, pain medicine, or, have you found that your algorithms can correct those?
We have.
That's great. Then second question is, with the data itself, sometimes the data itself encode and have biases.
Oh, for sure.
So how do you correct for those? Thank you.
I mean, it's part of my answer. Perfection is outside the human condition. If you want to impact the world, you have to accept imperfection. Of course, there's bias, significant bias. But what is the answer? We're not going to do anything? I don't think that's the right attitude. So we, and these methods give sometimes incorrect answers. Of course, we make correct answers relative to humans. I have evidence of that, but I have evidence of the following. So the way we have a recent paper where we try to tackle de-biasing the data. Still ongoing work. I cannot say we have, but the answer is, something I learned in 40 years is that I accept imperfections, and we go ahead with it.
We have one more question. Please.
Thank you, Professor. You talked about different examples on agentic AI, such as HIME, in medical imaging, for example, for image segmentation. I work as a chip designer for medical chips, so X-ray chips and
at MIT,
at analog devices. So these kinds of chips.
I know what analog devices.
Yeah, and so we one of the questions that we are asking ourselves now that we are moving a lot of the computer processing to on-prem rather than offline is how can we train our models using unstructured data that's coming from physical AI. So instead of training with the image,
I have some examples on that. We have. I didn't talk about it, but we have written a first paper of its kind of predicting hurricanes, and the data comes from, wind data, physical data. I mean, it's feasible. I mean, I'm not saying we did it fantastically well, but it's not outside the realm of capabilities to do that. I think this is a great future. In fact, I have seen some works, people have continued with strong success. That's not I think that's a good way, from what I know. I'm not an expert on these matters.
Thank you. So, for example, in that case, with wind data, what kinds of challenges do you envision physical AI will encounter when using this kind of physical AI?
I have limited experience. I don't want to overstate my, I know something, but I don't know. So it's very sensitive. Robustness is relevant there. For example, because the wind speed comes and changes, sometimes what you measure from the wind is not so accurate. So we actually applied Robusta methods to make certain that even if there are small errors, and if you don't apply robust methods, this thing is not accurate. So that's something I know. I'm certain there are many others that I do not know. I'm sorry that I cannot be more, but that's the degree of my knowledge. One more?
Yes, we can do one more, of course.
Actually, two more. Yes?
Congratulations as one of your former students.
I remember.
This is a great honor. You deserve it.
Greeted you.
Yeah. So my question is around real-time monitoring, so of data as it comes in that might, change the decision somehow. So like in a test, and when you have tests coming in like a CBC, those aren't, real-time necessarily, but other things like maybe
yeah, I know.
Something.
You have vitals, the temperatures, and
yeah. So or an intervention. So like let's say that you have.
Yeah, I don't have a lot of experience with real time. I have one experience only actually in a hospital in Toronto. A very good hospital actually, the Children's Hospital in Toronto, where they had real-time information for the children in ICU, to be able to have early detection if something goes wrong far before it's a crisis and you cannot. It was successful. It wasn't particularly, this was 3 years ago, sophisticated, didn't use HIME, we used more elementary methods, but it was helpful. So look, AI would affect medicine. If this does not happen, I'll be shocked, and I haven't been shocked easily. Now, the nature, I do not know, but the fact that it will make a difference, I have no doubt, and real-time monitor is also relevant from what I have seen. But again, one study, not gigantic numbers. How about from this part of the room? Come
Please,
on, guys.
yeah, one last question.
Okay.
Thanks. Thank you, Professor.
You're welcome.
I also remember taking your optimization methods class. It was very good.
You took it with me?
Yeah, I took it with you.
Okay.
I survived.
Imagine that.
Yeah, my question is about the, in all these different areas where you've made contributions, just how you interface with professionals in like healthcare or agriculture, and kind of how you convince them to believe in what you're providing.
Well, when I was young and inexperienced, I used to believe merit alone carries the day. I have news for you. It's not true. So I start meeting with healthcare. Today I actually canceled the meeting because I said I should go directly. But yesterday and the day before, we have meetings with the professionals we work. I start my day at 7, as Stephanie very well knows, my assistant. 7 to 9, I have half an hour calls with doctors, with agricultural firms, and so forth. And it's not to talk abstractly. The team members, myself, we talk about issues we face. And what I have found is that, to give an example, when we started with some physicians, we, of course, I'm reasonably well respected. I have white hair, but there was doubt. The senior doctor was very positive, but the other 5 were not. We start meeting weekly for half an hour about SAVR versus TAVR. These are the senior leadership in cardiology. Every time we met, we data, ideas. They start contributing. They now became owners. What happened? When we finished the job, they wanted to present themselves. They didn't let me, or, I said something, but the vast majority, this is a transformative experience. That is, if you want to impact, you better engage them. If you take the point of view, we are these MIT experts, we know better than anybody else, I wish us luck. I used to do this and I failed. And then I said, why did I fail? And So that's my advice. If you want to have impact in the world, work closely with the people you're trying to impact.
Thank you.
Similarly with Panama Canal, actually. The guy who asked me, I was calling me twice a day until I understood what's going on, and then we model it correctly. So then when I presented next time, I didn't present so much, he presented. This is very, very convincing. Much more convincing than if we, the experts, so to speak, talk. Thank you. Thank you.
Thank you again, Dimitris. And I'd like to also take this opportunity to thank my colleagues on the Killian Award Selection Committee who made the outstanding decision to award our distinguished guest and lecturer this award. And I would like to invite everyone to the Nexus in Hayden Library for a reception that is soon to follow. So there will be further opportunities to grill our lecturer. You'll find friendly guides along the way. There will be signage leading you to the Nexus. I want to thank you all attending, and most of all, Dimitris, thank you, Professor Bertsimas, and congratulations again.